No, thank you very much. Thank you, Larry. No, the reason why I made that crack about Berkeley was because I knew that Charlie Towns thought this was a crummy idea. and you know, he said if you don't need to build something so big, if you're not really smart, you can get away. I mean, if you're really smart, you can get away with something very small. And we tried, and it just didn't work. Anyway, some of you were here, or were in Europe, heard this sort of talk without knowing the punchline. But this is not going to be very different. But what we were celebrating in Europe at that time, which was about November of last year, was the origin of the Einstein field equations and the struggle that had gone through in November of 1915 for Einstein to get those field equations. And I'm not going to start there. I'm going to start with something that happened about 6 months later. And that is Einstein was trying to apply his field equations, and let's see if this thing will work for me, in a paper in 1916, which was an application of the field equations. I'm not going to make you read all of this. Don't worry. I will quickly show you what's in it. But this was a perturbation calculation, a Näherungsweise of the field equations. And in that, he does all sorts of things over again. He does the perihelion advance. He shows the Newtonian limit. And he comes up with something new. He comes up with gravitational waves. And there's some interesting things in this. He's looking for solutions. I'm not asking that you understand all of this. I just want to point things out to you. And he's looking for solutions that, like you tell your freshmen about, namely things that go both in position and time. Of the field equations, he finds some. He finds some that are not zero. And it then says that he, in fact, even relates them, and this is where the trouble begins. He relates them to a pointing theorem, in which he shows that these particular metric coefficients, which are the way you finally do talk about gravity, you talk about the changes of space-time, and that these metric coefficients add up in such a way that they carry energy. And here is the pointing theorem. He even uses an I, the Minkowski metric, still in doing this calculation. But this thing turned out to be extremely controversial as life goes on, because it turned out to be very coordinate dependent. It wasn't really a tensor, and it caused a lot of trouble. And I want to show you what these field equations do look like, what these solutions look like. And what you're going to see in the next thing is a sort of amateur movie of you being at a little red spot in the middle of a bunch of dots that are distributed. And what you're going to see is a field that is a gravitational wave coming at you or going away from you. And what you'll see what a gravitational wave does. It's a strain in space. And here's so that you can visualize it. I hope you can see it. That's where you are, and you can see things are expanding in one direction, contracting in the other. That was a little fast. Let me show you a little more slowly. I would go back to the movie. Here you can see that it's stretching one way, compressing the other way. But the thing that's characteristic of this is that a strain pattern at any one of these things has equal ratios of the displacement change to the displacement between the dots. And that's the important thing in visualizing this. Here's it once more, and then I'll let it go. Okay, so he makes a rather interesting mistake, and I want to show you this in these. This is the next slide. And these waves come in two polarizations. Since it's a spin-2 field, that wasn't the way it was discussed in those days, but that's what it is. They're 45 degrees to each other. These are these plane waves that are moving at the velocity of light with this interesting strain pattern. And then he writes something which really got him into trouble. And that is that he now is trying to relate the sources of the wave to the thing that generated, the generation of the wave by matter to making the wave. And here is then, he says that the things that makes the wave are the third derivatives of the moment of inertia changes in time of the different parts of the distribution of matter. So there's accelerating matter makes the waves, but it's only specific shapes. But this one is a very interesting one. He got it wrong. If you notice here the different coordinates transverse to the direction the wave is going to propagate, and they're all positive signs. So it turns out here what happens is that he has a thing that if it was spherically symmetrically exploding or contracting or expanding, you would still get gravitational waves, which is not right. And so Birkhoff's theorem came a little later, and even it violates Newton. So he makes quite a significant error here. Later on, he writes a thing which is lovely. This is in 1918. he says, in my prior Darstellung, which is a presentation of this, I wasn't sufficiently durchsichtig, which means transparent. But on top of that, I made a dauerlichen Rechenfehler, which is I made a regrettable numerical error, which is not true. He made a really big physics error. Okay. And but nevertheless, now what he does is he gets it right. Here's the quadrupole formula in that ancient notation, which we'll fix up in a second. And here he now is that same formula that he had wrong. He has now a difference in the moments of inertia. And this does not radiate spherically symmetrically. And he has a forgivable factor of 2 error in this. That's forgivable. Okay. So now I want to talk to you a little. He says one more thing, which is really fascinating. And this is one of the reasons I made such a fuss about this in Germany. This is back to the 1916 paper. He looks at one of the terms, at one of these source terms. Again, here's a third derivative of a moment of inertia. And he looks at this here. Here's one of them. And he looks at A, and he says in German, he says, look at this. Here's this chi thing, which is tiny. It's 10 to the minus 27 in CGS units. And on top of that, it's also multiplied by 1 over c to the 4th, this whole thing. And so he comes and he says this, and this is an English translation of it. He says that this is never going to amount to a hill of peas. I mean, it's just so small, it doesn't matter. And it's never going to have a role in physics. And in 1916, that's probably quite right. And I want to show you that. And that's what this is. This is the same thing all over again in modern garb, okay? Here is the same pointing relationship that is the controversial pseudotensor. And now you can see what they are. The H's are these strains. And this is the thing that relates intensity in the wave to the strain itself, the time derivative of the strain, and here are the 2 polarizations. And it's a square of those, just like it is in E&M. It's a square of a field quantity, and that's the field quantity is H. But here is a dramatic factor. When you put that in, this is what Einstein was complaining about. This factor is 10 to the 36 in CGS units. That's this thing. It says, well, if a little tiny change in strain makes an enormous change in the intensity, or invert this. You need an enormous amount of energy to make a little tiny strains. And that's the problem, and that's what drove him. And so now the thing is that there's a nice way of combining the quadrupole formula, which is now, this is the same formula he had in his 1918 paper with a factor of 2 corrected, but now written in modern garb. And you can see it goes to the omega to the 6th, and it has the mass squared. This is the moment of inertia squared right in there. And then this 1 over c to the 5th. By the way, a lot of these factors are the same in E&M. Turns out that the thing you would change in E&M is you convert gm squared into the charge squared, and that's it. And you get an interesting thing. Those of you who have looked at this, you'll find out that you get the same formula within factors of 2, but the angular distribution of the radiation is entirely different. And I keep asking theorists who are smarter than I am about this, why is that? And they say it's tensor. It's not a vector. And that doesn't explain it to me. I mean, there has to be a better explanation than that. But okay. Anyway, here's a nice formula to help you try to make your own estimates about how big is H from things you can calculate for yourself. And this is what Einstein must have done. And I was asking the people at that meeting, could they have evidence? Could they find the back of the envelope calculations that were being used to do this? And here's the easy way to calculate H. It's, again, order of magnitude, but this is the gm over rc squared, which is the Newtonian potential divided by c squared. So this is the mass of the system that's being accelerated. This is the distance you are away from it. That's Newton's constant, and that's the velocity of light squared. Multiplied by a velocity squared, beta, that is not a spherically symmetric beta. It's a beta that has a quadrupole character. It's tangential. So that's, for example, if this is an orbital thing, that's the orbital velocity. And so what Einstein must have done, and this is the first example which tells you that this is going to go nuts. He loved trains. I was hoping I could find this. You know, suppose you take trains and collide them together. So you have something like the order of, you take a quadrupole moment, which is 2 trains colliding. Let's make it 2-car trains, something like that. Colliding together, 10 to the 5 kilograms in each car. The velocity might be 100 kilometers per hour. Sort of that trains existed in 1916 that could do that. And then you have to go to the radiation zone. You have to go out to a distance. If the train collapses in, let's say, a fraction of a second, you go out a distance 10 to the 5 kilometers, and you find out what's the value of H. Put those numbers in, and you will get an H number that is really absolutely ridiculous. It's 10 to the minus 44. And I'm sure Einstein must have done that number for himself. And he said that alone was enough to show him that there was nothing he could imagine that could measure that. Or he might have tried to do this. He might have taken a binary star system of the kind that he might have known about in 1916, which had a period of a day with solar masses, maybe 10 kilolight years away, although the galaxy was not yet known at that time. That kind of dimension was known, that you were talking about something like this. And then put that in and see, could you, with a telescope, with a system like that, could you see its aspect change? Could you see it, could you see it shrink? And you couldn't. I mean, the K time for that to do gravitational waves just from that quadrupole formula is 10 to the 13 years. So there was no thing he could imagine that would, an aspect change that would cause. And so it turns out that he was absolutely right. In 1916, neither astronomy nor experiment could have done much about this. But there was 100 years between then and now. And that 100 years I want to talk about a little bit. And I don't expect, again, that you get everything in these pictures, as I'm going to point out various little high points in it. And that, I'm going to give you a little bit of history of this thing. And here is Einstein. And the first guy who noticed there was real problems was Eddington. And Eddington tried to use that pseudotensor. And he got different answers for different coordinate systems. And he said, this is all crazy. And in fact, he coined a word. He thinks that gravitational waves propagate with the speed of thought. That's what he thought. Okay, and there's a book written by Daniel Kennefic of that, with that title, about the history of this field. And the other thing is he tried to solve the binary systems himself and found that with the approximations that he had to make, they accelerated. They gained energy as they lost gravitational waves. So he threw the whole thing out the window. He was a very important guy. He made Einstein famous, and this was the beginning of sort of this oscillation that went on. And you'll see that what I've done here, I've organized things in terms of blue being theory, green being observation, and red being technology. And these things over the 100 years have tended, and this only goes from 1916, let's say, to 1960. Then he walk you through a little bit of the technology. Vacuum triodes were sort of came in there. Lock-in amplifiers that I've given this talk sort of halfway once before. Many people don't even know what a lock-in amplifier is anymore. But there are some. And then here's the business of stabilizing cavities, stabilizing klystrons or oscillators with cavities. And here's, let's say, the maser, for example, and the atomic clock. These are all developments that happened in this. But all during that time, there was a tremendous oscillation of whether one believed in gravitational waves or not. Here's Rosen and Einstein, who wrote a paper. There's a famous story behind that, which I won't go into, but it's fun to read. It's where they tried to get an exact solution of the Einstein field equations, which was a pure radiation field. You could be able to make that. And they got something which didn't work. And they submitted it to physical review, and the editor sent it to Robertson, and Robertson found a mistake in it and said that, no, they had the wrong answer. But anyway, they had come to the conclusion. Nathan Rosen, in particular, had come to the conclusion, had convinced Einstein, look, these waves were nonsense. Okay, and Einstein agreed with that for a while. And he oscillated about a lot of things. For example, here's the other big development that happened in that epoch, just before the war, as Oppenheimer and Snyder began to look at what would happen to a star that had gotten to the point where it got so massive that it couldn't sustain itself against gravity anymore. And they found out, in fact, that stars would collapse, and they didn't call them black holes, but they would be singularities. And so that was a big deal. The thing that started straightening all of this out was in 1957. Here's Feynman making a comment saying, look, all this field needs is a little experiment, less mathematics. That was a thing that he stated before this Chapel Hill conference, which was organized by Josh Goldberg. And that was a watershed in this field. Because what happened at that meeting was that there was a Gedanken experiment of a very crude variety. It was brought up by Bondi and then also, but not so much by Wheeler, but the idea that is, look, suppose you had a bar and you stuck little beads on the bar and the gravitational wave stretched they pushed on and they were talking about forces, which were a little complicated. But suppose you pushed on those beads, they would heat up that bar. And consequently, yes, there was work done by the gravitational wave field. So consequently, thinking about it in terms of something real instead of something just mathematical. That was a big thing at that meeting. And in fact, Bondi and F.A. Pirani, who influenced me a lot, and Wheeler, began to really think about trying to figure out what you could do to make a measurement of a gravitational wave. And that was done then by Joe Weber. Here's Joe Weber, who did it differently than we're now doing it, but made a great big bar, and these bars were acoustic resonators, and they were then stretched and expanded by the gravitational waves, much like this model. And the idea was that you would then have time after the gravitational wave went by to listen to the bar singing, because it would be started in oscillation at a normal mode, and that normal mode had a high Q. That was the idea of the detection. And that got the field into a lot of trouble. what happened is Joe thought that he had seen gravitational waves, and he published papers about this, and it turned out that it was his idea. Certainly he deserves credit for starting the field, but that experiment and the things that followed made a great deal of difficulty for everybody who followed him. The other things that happened at that time here, for example, is the first real explanations of the black holes with Kruskal coordinates, not just the Schwarzschild coordinates, and then here's Kerr a little bit later, right in here. This is finally explaining a rotating black hole and trying to find out where the singularities really are in a black hole. Found out it's only in the middle. And here is a person who influenced all of us who are working in this thing, and we'll get to that in a second, is Bob Dickey, who did something which you'll see over and over again when I get to talking about LIGO. He invented the idea, at least for us, that you control a mechanical experiment by servo systems. You never let a mechanical system move. What you do is you make a system which is controlled by a servo system, and then you read the servo signal out. You don't let it move. And that way you damp the system, and you do a lot of other good things for it. And so then there was, and almost a point that I want to really get to, which is right there, but here is there was the idea that, and this is where the beginning of this idea of LIGO came from. None of us knew this. Gerstenstein had the idea in Russia. He did the following solution. He solved what were the field equations. He used the Einstein field equations and looked at what would happen when you have a gravitational wave going through space and you happen also to have an electromagnetic field in the same region. What do the Maxwell's equations look like when they are driven in a flat space with a flat space and a gravitational wave? And you get side bands, and he was really the first person to really think about that. Here then is the thing that happened. Here it was in a course that I gave, and I will walk you through this because, and that is I was teaching a relativity course for the first time, and what I knew about relativity you could stick in a thimble. I mean, I didn't know very much, but I couldn't explain things, and what the students were most interested in were trying for us to explain to them what were the Weber experiments all about, because that was an exciting thing at the time. And what happened is that I came up and I said, look, let me do this all over again, and I want to show you what the basic idea was so you can see it. The idea was, here's now, take a gravitational wave and see if you can time the light that goes between two objects that are sitting in a flat space, which is on top of which is a gravitational wave. So I have to set up a coordinate system and a metric to do that. It's not hard. Here is the interval between events, and we'll talk about it in a second. Here is the Minkowski metric, and here is this additional field metric. Here's the Minkowski metric, and you take a particular direction for the wave. It's the one direction, so the nasty stuff that the wave is doing is in the 2 and 3 direction. And here are the two polarizations. That's the plus polarization, these two, and here is the cross polarization. Those are what you start with. And here's the Gedanken experiment you do. This is what I gave the students to do, and they did it. And we all did it together. And it was the idea, do the following. It's a very cleanly posed problem. And that was set up a coordinate system where the masses don't move, and here they are. The masses keep fixed coordinate values, and you have good clocks. These are perfect clocks that keep perfect time. And it turns out in that particular way you write the metric, the clocks keep the same time as the coordinate time. Proper time and coordinate time are the same. So the clocks don't get messed with. And now what you do is you say, take light and send it from one guy to the other, and let's see what happens when there is a gravitational wave and when there isn't. So here it is. The interval between the sending of and the receipt is delta S squared is equal to 0. That's still just like in special relativity. Here is the thing broken into its coordinate components. This is the distance between the masses, and it doesn't change. Here's the metric components, the Minkowski part, the wave part, and this is the time. And so now let's make it easy for us so that we have the time so that it's very much shorter than the period of the gravitational wave. You don't have to do this. That's not essential, but just so you can do the arithmetic. And then h is very small. Now that's always true, unfortunately. And so you just solve this equation, and you wind up with this equation. Here then is the time it takes light to travel that distance. And that's the distance defined by these two masses, and you'll get just these two terms. This is a fixed term, that's the length. And you divide this out, work it out. This is the inferred separation. And you see that it changes with time, just like the metric divided by 2. And that then is the measurable quantity. And the reason why I can make a fuss about this is because it stopped people misunderstanding this, stopped the field of looking for gravitational waves with light for about 10 years. They just said, look, here's space stretching, wavelengths are going to stretch along with it, you're not going to see anything. And that is just totally wrong. So here then are the people who did this. This is back in the 70s, and these were the groups. Here, let me show you the initial idea. This was the idea. This was the Gedanken experiment turned into a real thing. What you do is you make a laser interferometer, and we'll get to that a little more. But this was a vacuum system. You send light in from a laser, it hits a beam splitter, and then it goes back and forth in something called the delay line in here. It goes through a modulator to make the light have a fringe change, a phase change that's high frequency, so you can do it getting over the 1/f noise of a system, and the same thing again, and you can detect this on a photodetector, which is here, and then you do exactly what Bob Dickey said. You use that, correlate it, feed it back to these masses, and hold it steady. Keep that mass from moving, and that whole system is rigid as the gravitational wave goes by, and you have a signal you can play with. And here are the first 3 people who work on this. Dave Shoemaker is still on the project. The people who then added an enormous amount to this idea were the people up here. The German group, which was at Garching at the time and part of the Max Planck Society. Here's Heinz Billings. They were working on bars, and they were at a crucial decision. Should they go on with making bars after Weber was found not to be true, or should they make better bars, or should they go into this new technique? And they found out about this because the NSF sent my proposal to them, which is fine. And here are the people. The Europeans, that was an etiquette that wasn't observed so much in Europe. They called me up in a very straightforward way, said, look, do you have any students who worked on this thing? And I said, no, we don't have any money. I mean, that was the problem. And so so here are these people, and they've made some vast improvements to this idea. They started hanging all the masses. Here only the masses that are hanging, only the end masses in the middle, and they divided this all up. That was his idea. This guy thought of putting light back. We'll see that in a minute. It's called power recycling. I'll explain that better when we get to it. This guy worried about the light scattering in it. Maischberger worried about, again, hanging. And Frau Schnupp got rid of these modulators, which are a pain when you start putting this together. She put them on the outside and did some very tricky things. So this group made vast improvements in this and to make it a better system. The Scotch group, the Glasgow group, and here's Ron Drever, who ran that group, also had the same experience. Their experience was that they were going to make, they had bar experience, and they were now thinking they'd gone to see the German thing, and they looked promising to them. And so here are people who added things. Harry Ward added the idea of how you stabilize the mirrors. We'll get to that. A different modulation technique to tune the interferometer called signal recycling. Jim Huff was just generally a superb guy, and this group made enormous advances in this. So these 2 groups did far better than we did at MIT with the basic idea. They had some money, they could do it. And in fact, Ron Drever then wound up at Caltech, running the thing at Caltech. So anyway, here's the basic idea with some of these ideas in it. So I just walk you through this. This is the critical thing for the interferometer. Here is fundamentally a Michelson, but now what happens is here's the laser. This is the new mirror. We'll worry about that in a minute. Here's a beam splitter. And what you do with the beam splitter is part of the light gets reflected from this, and it gets bounced back and forth. In this case, it's a probably probe cavity. But you make that cavity the same as this cavity, so they have equal time in these 2 cavities. And so the light gets reflected, comes back to the beam splitter. Here, the light gets reflected from the front, gets back to the beam splitter. One has been transmitted by the beam splitter, the other one has been reflected. Then, on the back side of the mirror, they cancel each other. You arrange it so that the paths and times are identical in these 2 arms. And if that's the case, once you solve the Fizeau equations, the Fresnel equations rather, on the beam splitter, you'll find out no light goes to the photodetector. The 2 fields cancel each other if the times are identical. And under those circumstances, no light goes here, and all the light goes back to the laser. And that's where this new mirror comes in. That was invented by both Schilling in the German group and also by Drever and Drever in the Scotch group. And the idea here was to match the interferometer to the laser, meaning that you make it so that the laser light, none of it gets reflected back to the laser. What you do is you take that light, which is coming back out of the interferometer, which is almost all the light, and add it to the light of the laser in such a way that you phased it properly, making the transmission of this right so that no light gets reflected to the laser and it all goes back and making a single cavity out of the entire interferometer. And that takes it so that maybe if you have 10 watts of light here, you have tens or hundreds of kilowatts of light in the arms. Okay? And that's a very important trick, and we'll show how that eventually got into the whole system. So here then is the noise budget of the first interferometer we built, of the big variety, of the 4-kilometer thing. I just want you to know what went into that. And then we'll get to what the discovery was. And the thing is that here is what's plotted here is the frequency of the signal you're looking at. And this is not H, but it's the spectral density of H. So it's a strain per root hertz. So if you want to get back into a thing that is strain, you would multiply, for example, the point on this curve like here with 100 hertz. You'd multiply this value, which is 10 to the minus 23, in strain per root hertz by something like a 10 to get sort of the RMS value of H. And so you can see what the fundamental limits are in this interferometer. One of the limits, and this is the quantum limit, I'll point that out to you, this curve attached to that curve. And this curve here has to do how well can you measure the phase of the fringe at the photodetector. And that improves as you increase the power. So this goes down when you increase the power. Over here, this, which in this initial interferometer really didn't play much of a role, is the radiation pressure fluctuations on the mirror. They're the same as the Heisenberg microscope that you teach in a quantum course. And what that does is it's making stochastic forces on the mirror, and that'll get worse as you increase the pressure. So for each, as you increase the power. So there is an optimum for value for this, and this is called this will play a big role in advanced LIGO, as you'll see in a minute. Then there are other things, like you have made, let's say, this wonderful device that makes very tiny measurements of the fringe, 10 to the minus 18 of a meter. So 1,000th of a size of the nucleus. So that's sort of the level that you can do the measurement of the fringes to. But now you have other problems. You have to make sure that the mirrors that you're looking at don't themselves move by more than that, not due to the gravitational waves. That's a much harder thing to do than the optics, it turns out. And you start off right away with the fact that the ground is shaking by a micron, which is 10 to the minus 6 meters. And that is, you need seismic isolation. You'll see that you do that in spades. You have to have lots of it. And then there is thermal noise, Brownian motion, the thing you see under a microscope in a biological system. That's also going on. We're not operating this at very low temperature. So the suspension makes thermal noise. And so that's another piece. And that's the envelope that was designed, that made the first detector, gave it its sensitivity. Here are some other noises that are very important. You have to have a vacuum. So here, for example, gas in those long arms, 4-kilometer arms, has to be better than 10 to the minus 9 torr of hydrogen. That's sort of where we operate. And if you don't have that, you get forward scattering from the gas, which then causes phase fluctuations in the light. Here's the thing you can't get around, and this is the reason why it's very important noise, and the reason why people think of doing this in space. And that is that you have another force which, after you've all done, and this is not understood by everybody, you've got a mirror. Let's say here's a mirror hanging. And now here's ground waves that come along, seismic waves that come along. And what they do is, besides shaking everything, the acceleration is easy to get rid of. That's an acceleration relative to the inertial frame. You have a reference for that. That's beautiful. But you don't have a way of shielding the following problem. Namely, the wave comes along and it compresses the ground and expands the ground, compresses the ground, expands the ground. And a compression on the ground here pulls on that mirror more than a place that has been expanded. So consequently, you have Newton, just plain old Newton gravitational forces pulling that mirror back and forth. And that's a key problem, and that you can't do much about. We have ideas for how to do that, but that's the reason, one of the reasons, main reasons why people made LISA, which is a project that would do this in space. So, let me go on. So, let me quickly say some more about, I'm about on time for this, at least for my own time. There are other things I want you to notice in this picture. This is now going to 1990. Here's this whole business with electromagnetically coupled antennas and that broadband antennas. Here's the committee that met, the NASA committee, to look at what could the space program do for gravitation and cosmology, and people on it were interesting. Charlie Misner, Bob Pound, and Peter Bender, and I was the chair of that, but what we invented on that committee was LISA, and Peter went and ran off with that. That's good, delightful. And then here is a very important development for the whole field, but I can't give it all the time it deserves, and that is that actually a system was found of two neutron stars that were going around each other and carefully measured, one of them being a pulsar, looking at the pulse arrival rate of that pulsar for something like a decade and a half. Hulse and Taylor measured the fact that you got the orbit absolutely down to a gnat's eyebrow and found they had to include a gravitational radiation reaction to get a fit of the pulse arrival rates to the theory of the motion. That won the Nobel Prize in 1993, and it was the first discovery, as far as I'm concerned, of gravitational waves, but it wasn't a direct measurement. It didn't open up gravitational wave astronomy, but it proved that things were right. So here are some people who then invented another scheme for doing this. We'll talk more about that in a minute, and that is pulsar timing. We'll get back to that. And here are people who were thinking at what might be the very earliest parts of the universe, and how might you get gravitational radiation from that. That wasn't necessarily on the minds of these people so much, but Starobinsky, whose picture is in another place, was that way. And so what happened is that a big report was written in 1990, in 83, and at that point, well, we were asked by MIT, by the NSF, to write they put a report together, how much would it cost, was it feasible to build a thing the size of LIGO, with all the knowledge that was now coming from the prototypes. And we did that, and Peter Salson was an important member of that, and that's when the collaboration between Caltech and MIT was made. Right there, they together presented this big report to the NSF. And the NSF, especially with Rich Isaacson, who was the head of gravity at NSF, was instrumental in their stalwartness to keep this going. It's absolutely a magnificent story, which should be written up. So anyway, then in 1986, there was a nasty letter written by Dick Garwin, who was one of the people who managed to get rid of the problems of the bars. He thought it was all pathological science, and he asked for, if the NSF was going to be stupid enough to put $100 million at that time, that was sort of the price tag, into something as crazy as LIGO, they ought to study it well and make sure they're not getting ripped off, okay? And that committee, which with these two as chairs, did an absolutely magnificent job. They saw that every idea was right. They thought it was a wonderful field for the NSF to go into, and they said our management sucked. That's what they said. Okay, and it's true. It did suck. And they said, you get yourself if you want this to go anywhere, get yourself a director. And the next thing that happened is we got a director, and we wrote a beautiful proposal. There's the director, Robbie Vogt, and here's John Drever by that time at Caltech. Kip Thorne and I wrote that proposal with Robbie. And then at the same time, just about, there were effort in Europe that was started, same thing, and that's now led to the Virgo project. And then the Germans, the same group, but now with a new leader, was trying to do the same thing, but they couldn't get quite the money. But they got a 600-meter instrument eventually, and they also pushed LISA, and they won that. And then eventually what happened is that the person who really got the thing going was Barry Barish. I won't go into all the history there. And here are people, this is one person who was a real hero, who is a guy who really began to break loose the numerical relativity solutions for black hole physics, which now turned out to be extremely important to us. And then here are people who were, here's the current director, and these are people who have made LIGO work. Okay, so now let's get on to what LIGO really is. So what LIGO is now is part of a network, and we're trying to grow that network, and you'll see the reason for the network when I go on and explain our discovery. There's a thing that's missing in that discovery, which is not knowing exactly where this source is. And that's one of the reasons that you would like to have more than just LIGO, which has its two detectors, one in Louisiana and one in Washington State. There is this other detector, Virgo, which is in Italy, which was unfortunately not on the air by the time. They were busy fixing up their detector. And then there's a smaller detector, GEO, which isn't quite sensitive enough, but it is a development. It's very much like a prototype. Then there is a thing which will be on the air in probably 2019, 2020 in Japan. That's being built in the Kamioka mine, and that's a 3-kilometer. And this thing is just broken loose because of the discovery in India. One of the LIGO detectors is going to India, and with this collection of detectors, we will be able to pinpoint better where the sources that we are looking at are, and then be able to communicate them to people who do electromagnetic astronomy, which is very important to set the context for what is being discovered. It's critical for that. Okay, so, and then here, so they quickly see here's the performance of this thing, and this comes back again at the end of the talk, is that here is the performance of Virgo in a last run it made, and this is by another one of these plots, frequency versus spectral density. Smaller, higher sensitivities down. And here is Virgo's performance. Here's the last performance of LIGO. And you can see that it went off like that. And here is the first performance of advanced LIGO. And you can see the big improvement that happened. Compare this with greenish line to the purple line. And you'll see it's about a factor of 3 in 100 hertz region. But it's vastly more in a critical region for the black holes. Down here at lower frequencies. And so where we picked up that black hole signal, it's a factor of 10 or more. Okay, so that's very important. I won't go into all of this until later at the end. But that set us into running. And here is the things that were changed. Big things to make that better at low frequencies was a much more complicated suspension system, not just one pendulum, but 4 in series. The other thing, which is maybe quite useful to people here, because you do biophysics with these tiny motions, is a active vibration isolation system where you use seismometers and forcers. And what you do is you null the seismometer in a servo loop. And you make that as a platform for this suspension. There's that suspension. So this is a thing that actually senses the ground motion, kills it on the platform. And that was very important to get that low frequency performance. I won't go into the rest of this. That's unless you get it. I think I will. If you get at the end and anybody has patience, I will show you what this is. This is for fun. It's mostly you're sitting in the control room of LIGO and seeing how the noise is brought down. I don't think I want to do that. Only if you ask me for it. Okay. So here, now let's get on to the discovery. Yeah. And so here are the conditions that we imposed on ourselves, and were part of the experiment design. The thing is that you have to have the same waveform seen at both Louisiana and Washington within 10 milliseconds of each other. In other words, we believe the velocity of propagation is the velocity of light. It could be coming from any direction, so you have to give yourself the slop of plus and minus the velocity of light time, and that's it. So it turns out that we'll see in a minute that the time difference between the two signals was about 7 milliseconds. Associated with the fact that you have two detectors and seeing the same waveform, which is actually critical. The other thing is that each site itself has a whole set of environmental monitors. Monitors for wind speed, line voltage, magnetometers, microphones, tilt meters, seismometers, anything we know we can measure. And none of the signals that come out of this can be on or be making a signal that's viable or sensible at the time when we see the gravitational wave signal. In other words, we've used these as vetoes. And on top of that, there are, within the instrument itself, something like 100,000 other channels that come out. I mean, it's a huge, that's what makes it so complicated. There's pointing information, information about the laser, what's the frequency noise of the laser, what's the amplitude noise of the laser, 100,000 different pieces of information. And if those pieces of information don't look like they're on the money, again, you will not accept the fact that you have a detection. So those are the internal things we have, which many people didn't have in the earlier days. It makes it so that you begin to sort of believe that what we had. And here's what we found. This is now what you're going to see in the next 3 slides is exactly what's in the paper that was written.
Some idea, which I don't remember.
Yeah, please.
The amount of vetoing that's going on?
The vetoing is very small. It's 1% of the data right now is being vetoed, it turns out. It's very little. But the protection is huge. Yeah. That's a good question. Thank you. You hear the question, what fraction of the data is the way I interpreted. His question is what fraction of the data is being cut out by the vetoing? It's of the order of 1% or so, 1% or 2%. So here's what we saw. Here's that signal. Now down here is a time. And you see it's a very short signal. It runs sort of 0.2 seconds. And this is the Hanford signal, and this is the Livingston signal. Here's the real signal. And you can see it, and we'll talk about what that is in a minute. I just want you, first of all, to look at the signal. And then here is that signal. Here's the purple one. The blue one is the Livingston signal, and behind it is the red signal, which has been translated by 7 milliseconds, and on top of that, inverted. And the reason for that is the way the arms are organized. You have to include that. And then they sit on top of each other. And what you have to hear is something which you don't get out of that paper unless you read it very carefully. This signal has been filtered so that you can see it. I mean, by hand, you can see it by eye. The morning that thing happened, all of us could see it, but there was no fancy data analysis. And the filter that you needed to do it was nothing more than you have on your audio supply. Here is the frequency, and this is the amplitude of the filter. And yes, at about 30 hertz, it rolls off. It has a bass loss, and it has a treble loss. That's it. And then it has all these notch filters, a bunch of notch filters to take out the things I didn't point out to you in the 60 hertz line, other lines that are very, very narrow. There's no reason to make them so big that you can't see the signal. So this is the filter that was used to do this. And what that did to the signal is it made it look like it was coming down. In other words, that's an artifact, and you'll see why that becomes important in a second. Here is then 2 curves. This is now theoretical. One that's in the back is an analytic curve that's sort of shaded, and that's done for both sites. And then there is a numerical relativity curve based on the best fit of all the data and the data involves 15 parameters. For example, the masses of the holes, the spin of the final hole, the position, the distance, a whole bunch of things have to be fit for. And but now that's the best fit. And here's the residual between it doesn't matter if it's in the numerical one or the analytic one. This is the residual in both places, and the residual is small. And here's sort of the idea of how big is the strain That's 1, this point is 1 times 10 to the minus 21. That's about there. That's the amount of strain we were measuring. And at the peak value. Now let me show you what the signal was supposed to represent, as far as we understand it. And now there is no filter in this picture. And that's why it looks different. Here, this is what the theoretical curve actually looks like without that filter. That filter to make it so we could see it more easily. Okay, and this is the input. This looks very sinusoidal. It's changing frequency a little bit as the black holes are moving closer to each other. And finally, they get to the point where they're merging. And at that point, the peak gravitational wave output comes on. And then as the thing forms its new event horizon, you begin to see a ringing. Now, we did not see that with any great precision, this part right there. Yeah, there's something going on. I can't say we saw that, but we saw all the rest of it. Okay? And what gave it away that it was black holes is the frequencies. You could not do this with neutron stars, and you could not do that with a neutron star and a black hole. When you look at the chirp mass of that system, you need 1,000 solar masses if you want to make a neutron star do this within a combined system. So it looked very unlikely, and it didn't work out. And here are some of the sort of rah-rah kind of things that come of this picture. For example, here's the velocity. This is the velocity, the relative velocity of the two as they get closer and closer. This is the velocity of light. This is 0.5 the velocity of light right there. They get going on. These things, which weigh 30 times the mass of the sun, are moving at about half the speed of light. Unbelievable. And then here's a separation in terms of the Schwarzschild radii for 30, and they're getting closer and closer. Eventually, they hit each other. So that's the discovery, okay? And now let me show you how you dig for this, and how do you get the parameters that you were published. And there are two methods, and those two methods are described in the paper and may have confused you. And I want to spend a little bit of time so you understand them, because that's important for the future, okay? There are two methods. The first method you're going to see here is the method in which you do something where you don't know anything about the source. In other words, you don't know that it's a black hole, you know nothing about it, you don't have waveforms that you're trying to match or anything like that. What you use is the fact that you have two detectors, and what you're going to see is a little movie where you have this waveform, which is an arbitrary waveform. Let's say you measured that in Hanford, and let's take that same waveform. You're seeing that along with its noise, and you see that in the other detector. And the way you find this, and let me try to pull this over if I can get this to work. I hope I can. It's nothing very profound here. It's just a thing that shows you what's going on. You'll see that what's going on here is the cross-correlation squared, in effect. And you see, you're multiplying noises together for a while, and then you get to the point where they're superposed on each other, and then you get this kick. And it's not as good as what you're doing is you're multiplying signal times signal, but signal times noise and signal times noise. So you have a noise term. It's not the best way of doing it, but you do not have to know anything about the signal to do this. And that was the way we found it. And that has a latency in the system of a few minutes. In other words, we can, based on this thing, we can tell astronomers we have seen something. Okay? The other way, and by the way, what is this curve here?
Ray, is the time in milliseconds on the bottom?
What?
Your delta T, is that in milliseconds?
Let's not worry about the time scale. I think this was all done by, it's arbitrary, okay? And these are fake signals, they're not real signals. So I mean, it probably is seconds, but I don't want to vouch for it. It really has nothing to do with it. It's just, you want to see what you get when you do this cross correlation. But this is more important. This actually tells you how well this works. Now I'm not going to describe both curves to you. The one that's important is the green one. And that also gives you the signal noise. If it was Gaussian, the statistics that remains. And these curves are curves that you do when you do not have a signal there and you keep cross-correlating. And you keep doing it all over times, over and over and over again, different times. And you get a curve that says that's the signal noise that you have. That's down here. The signal noise improves. And this is the number of events in that particular sample that do that, have that signal noise. And so here are places where they were coincident measurements made, coincidence measurement there, and then here is the event right there. And that event has a signal noise with this technique of about 20 to 1. And you don't see much else here. This is pretty much falling down. I don't want to go into this unless you ask me about it. It really doesn't add anything to it. Okay, so here's the other method. The other method is one where you actually use all the knowledge that you think you have. Namely, you assume, in this case, that you have a binary coalescence. You have a waveform that you have from either numerical relativity. I mean, you use something like several 100,000 templates. And and this is computationally very intensive. And what you do is you take each one of these templates with a different set of these 15 parameters and cast them, do the same thing, do a cross correlation with the templates over the waveform you have. And now, let me show you that one. I mean, this is the same deal. I think it's a little sort of silly of me to do this twice, but okay. And here you see the same thing. It's the same thing. Now what you're doing is you can see here's a noise-free waveform. It eventually hits that one. And then you'll see a very significant peak here. And that's sort of what happens when you get a lot more signal to noise. You're not multiplying noise terms. And so consequently, in this particular situation, you have, this is the background right here, doing it over the whole data set. Again, I don't think I want to, I can tell you what this is because it's simple. But here you can see that these are the backgrounds. But this is you're coming down and you get to the low event rates of sort of 1 per run. And there you see something that's a little off. Here's something which probably is, and we in our paper analyze that both with and without that point as being a real, we solved for it what it is. It's a so much smaller black hole event, black hole collision. And here is that event, and it has a signal to noise now of about 24. Okay? And so, and that's, by the way, how you get all the parameters that are about to be fit. You do that with this over and over again. Okay? And so if you now want to calculate a rate, this is the way this is done, the rate at which, what is the rate of accident? What you do is you take the correlation time, and that may be the length of the pulse that you're looking for, and you say, let me divide that by the total length of time you have. That's the fraction of time you're using up, and that will be the fraction of time that you would expect to see something correlated. And you make each one of those time intervals one correlation time apart, a new experiment. That's how this works. That's how we get these times, such that you get something like, for this particular event, it was once every 200,000 years, this apparatus will produce a thing like that. Okay? So we felt that was pretty confident. It's a 5 sigma result, which for most people is good enough, I think. So anyway, that's the, and here is sort of what came from the fittings. And that's still going on, by the way, and I'll give you, this is sort of in process. If you plot the mass, this is doing multiple fittings, doing it over and over and over again, and with a Monte Carlo technique for doing the sampling. Anyway, here is a plot of the contours for what are the two masses you began with, and here is sort of peaks. This one peaks at about 30. That one, a solar mass, is about 35 for that, and you get this sort of peak in there. And what you find out, what?
You plot 2 out of 15, you're holding the others fixed at their...
That's right. What you do is and you have cross terms, and you have to keep worrying about them. You're absolutely right. And so that sets for you what is, and it sets for you a calculation you might want to do, which is what is the spin of the final black hole, and what is the mass of the final black hole. And that turns out to be sort of in about 62 or 3, and it says the spin is not the maximal spin, it's around, well, it's the spin really that's associated with that orbital part that came together. We cannot tell you anything about the spin of the individual black holes that came together for a funny reason. When you do this, and you can see that in this plot, it turns out that it's either face-on like this or face-on like that to the detector. And then there is very little precession that comes about because of the spin-orbital coupling. But that's a very big term, and other systems, and you will see more of them later on, I hope, will show this precession. This particular system did not have that. And so we could only solve here for 2 things. We could solve for the distance, which is sort of 400 megaparsecs, or 1.2, 1.3 billion light years away. That's where this event took place, and it's either face-on or face-on the other way. And what it says when you put the 2 masses together, that these peaks together and this width, you find out about between 2 to 3 solar masses of energy have gone into gravitational wave radiation. Unbelievable amount. And if you sit that and use that, just look at the total luminosity in visible light, or total E&M luminosity of the whole universe during that 0.2 seconds. You find out this exceeds that by something like 50. I mean, it's the brightest thing in the world.
It's determined by the amplitude.
That's right, exactly. It's really determined, well, together, how much mass is lost too. Yeah. And so lastly, here's the thing that didn't do so well, and that's partly because we only had 2 detectors. And that is, this is the area of the sky. The South Pole is a little hard to find. There is the South Celestial Pole. And this is the error banana that's associated with this having only 2 detectors, and it's not very good. I mean, you get most of this from just knowing a little bit about the antenna pattern. There isn't much of one. But the other thing is the time gives you the cross dimension here, the dimension this way, and that's blown up in here. So we didn't do very well. On the other hand, people now, and this is now published, have looked at what was coincident with our event. And here is sort of a tiling of that same thing. It turns out with different techniques. It's a little hard to read this, but I can't tell you. But I know that they were both infrared, optical, X-ray, and radio. And they found these are little patches over the whole thing. And nobody found anything of significance, at least there. There is one thing that might be significant. Einstein, the Fermi satellite thinks they saw something within a quarter of a second of this thing, and we can't say if that's right or wrong. It's just the positioning is not good enough. But they will, I don't know, there's a paper being published or being written about that. Here is the neutrinos. Here's that same thing in a more conventional projection of the celestial sky, that banana. And here are some neutrino events that happened that don't seem to fit. So they don't think neutrinos were, this is from the South Pole, from the ice cube experiment. Okay? Okay. You're not falling asleep, so I can see that I can spend another 5 minutes probably, but that's it. That's all I need. There isn't, look into the future, there isn't just black holes. I mean, we're going to have a lot more capability of looking for black holes as we improve the detector. And let me say something about all of this. That what we're measuring when we measure gravitational waves this way is we measure the amplitude of the wave. We don't measure the intensity. So consequently, as you improve the detector by a factor of 2, you look twice as deep into the universe. That means you get a volume change of about 2 to the cube, or 8. So each factor of 2 improvement in the detector gets you 8 times more rate. And we still have a factor of 3 to go in the detector before we're at what are the limits for us. So we should have, if things go well, if we see an event every month, sort of which was a number that will probably bear out, of black holes, by the time we get done with getting the detector at design limit, that's the advanced detector, we'll have an event a day, something like that. So that opens the field finally into astronomy. And as Lars points out to me, keep an eye on that. Don't worry about other things, astronomy. Okay. Anyway, so there are other sources too. And the thing that we thought we were going to see first was the neutron star binaries. But that's not what we saw first. We saw these. Nobody could predict the number of those. So that's just wonderful. Then there are other things. That a supernova transient detection would be spectacular. That would tell you more about supernovas, actually more than most things that are known now, because it would tell you the inner dynamics of what really goes on in a supernova. But as you know, supernovas aren't that frequent, and we don't get supernovas strong enough. You have to use those in our own and neighboring galaxies. That's about as far as we can go. And that's the way now the numbers turn out for supernova. Then there may be, just individual black holes as they form. You might see the normal modes of oscillation. These are these things that are the wiggles that you saw at the end when it became quiescent. A thing that's a very active source that people are looking for, and we have been looking at and we will continue to look for, is pulsars themselves as CW sources. And that's due to the fact that the magnetic field of a pulsar may not be aligned with the rotation axis of the pulsar, and you get a wobbling ellipsoid because of the compression of the star by the magnetic fields. It's a very small effect, but people will keep looking, and it would be a wonderful signal to see, because it will tell you a lot about neutron stars. And the other thing that comes from neutron stars is right here. When we do ever get to neutron stars colliding with each other, which we should see, you then have this business of watching them going on for very much longer than the number of oscillations you have, many, many more than you have for that black hole we detected, black hole pair. And you can then actually see the distortion of the neutron star by each other, the gravitational distortion of the neutron stars by each other. And that will give you some feeling for what might be the equation of state of nuclear matter. That's the thing that has been in the agenda that we've wanted to do for years. Okay, and lastly, and this one is sort of, I got into this business partly because I thought you could see the stochastic background from the Big Bang. I think that's unlikely now, knowing more than we did at the time when we started all of this. But you certainly will see a background from foreground sources, and that's one of the more interesting things now that we know they're black holes. What happens if you look further, as you start looking at a unresolved set of black hole sources? What does it really look like? And we don't know enough about that. We clearly don't know until we have more sources to look at. So those are things for the future. And I quickly want to say, what is the future? the future then is, here is the design sensitivity for LIGO, advanced LIGO, and and here's where we are now. So these factors of, especially down in here, they're sort of, when you get done with all of this curve, and here's the Virgo curve when they come on the air, it will make a significant improvement. I think that factor of 30 is going to be about right in the rates. Then there are things you could do to the existing facilities that you can improve them by another factor of 3, and that's all theoretical at this moment. And we're going to try to see how much of this makes sense. And finally, both in Europe and in the United States, people are thinking of systems that are even better still. And I said something wrong to you, Lars. It's only enough another factor of 3, not a factor of 10.
So those last 3 are space.
This is what you could do in the 4-kilometer facilities of LIGO if you made improvements like using squeezed light, using cryogenics, using heavier masses, for example. Okay, that's not what we're doing now. But these are things where you build a new apparatus entirely. And for example, in Europe, they're thinking of burying a 10-kilometer triangle. And that's $1 billion project. I mean, you're not talking about way ahead, lots of money. Or in the United States, people are thinking about 40 kilometers instead of 4 kilometers. It turns out that's all ahead of us if we ever go anywhere with it. Okay, so the field isn't over by a long shot in terms of the technology that might be applied. And here then is the whole gravitational wave spectrum. As I've sort of hinted at as I was going through that history. This is frequency on this scale. We're running almost from, and I'll do it in time. And here's h. It turns out that here's LIGO at the frequency band of about 10 hertz, or a tenth of a second to 10 minus 4 seconds, and it will look for binary coalescences and what we've been talking about. Here's LISA, which looks in periods of hours to minutes, and will look at giant black holes, and also look at white dwarf binaries. And that's a project which we hope will get going soon, and with stronger American participation again. It was an American-European project, not until 2011, and then it got canned by NASA. The other technique is pulsar timing, and that's a technique which has sort of timing. The times that are valuable for it are 5s of years to months. That's about sort of the range. And what you're looking for there is you're looking at that you have many millisecond pulsars, and you're standing on the ground watching them all with their arrival rate of their pulses, and as a gravitational wave comes between you and those pulsars, it'll change the rate slightly. And the more pulsars that you have, the better off you are. And there are limits already coming from that technique, but no detections yet. And then finally, a thing which caused a big stir, but is really, to me, the most interesting of all, and that would be the primeval background of from the cosmic explosion, from the epoch of inflation, where you do have quantum fluctuations that may have made gravitational waves. And that was the thing that Weiss thought they had seen. And look, I fault them. Their experiment was a wonderful experiment. They should have had it peer-reviewed, and they should have not published right away. But the experiment was a wonderful jump, fantastic jump in the technology of doing that. And they're in the business now, a lot of other people in that business, and within the next 5 years, either there's going to be a very significant, I'll give you the numbers, we expect that R, that ratio of what's the tensor excitations of the fluctuations, of the density fluctuations to the scalar parts, that now has a limit that is, well, depending on how it certainly has a limit around a tenth. We expect fully that the ground-based things will do 0.01. And if they go on with balloons, which is being planned so you can have more spectral coverage, it'll be 0.001. And if they build a satellite, which will be discussed by the next decadal, it could go down to below that. It could get to the limit of what the foreground would let them do. So that's the thing which is really a very interesting experiment and a direction to go. And so that's the direction of the future. And here then is a summary for you of what are the major things I told you about. And that's sort of the end. I do want to show you pictures of people. That doesn't take long. And it is the first direct detection of gravitational by an instrument on the Earth. What that does is it has opened up astronomy. That's something you couldn't do with the Hulse-Taylor thing. You now have an instrument that can look at the waveforms, and you can use that as a way of looking at the rest of the universe. And you may find out some fantastic things. And we call it the dark universe. And the reason why it's so interesting is because this stuff just simply doesn't scatter. In other words, it goes through everything. It's so hard to detect. It also doesn't scatter. You can't deflect it. You can't do anything to it. But you can deflect it, yes, with other gravity. But you can't use other particles to do anything to it. So you can look all the way inside of anything. if it's radiating gravitational waves. To me, one of the most fascinating things is this, because I love the man, is this consistency of the field equations over a dynamic range of 10 to the minus 16. I mean, unbelievable that this should have happened with just pure thought. Every other thing I know of, virtually, except for Maxwell's equations, although that was all done in pieces too, was done by iterating with experiment. Unbelievable. I don't know if I admire it. It's just, to me, uncanny that you can do a thing like that. And then here are the more straightforward things, that the universe contains black holes that collide. We didn't know that ahead of time. And probably there are more black holes than we thought. Those are the two things that come from the astronomy side of it. Okay? And now let me quickly walk you through to people. This is the, this is the LIGO scientific collaboration with 90 institutions and 1,000 people, and you can find your favorite institution in these pictures. But that was something that Barry Barish instituted when he became director, and that has become extremely valuable because of a lot of the work that I'm talking about comes from that collaboration. And here's the Caltech group. This is now the LIGO lab itself. They're all standing in front of, and I won't point out people to you, but that's a significant group. Here's the MIT group. It's a smaller group, and that's just recently. And here's the group at the sites. This is to give you a feel for the kind of manpower that's required. These are the people at the Livingston site, and then finally here are the people at the LIGO Hanford site. So there's probably 180 people, something like that, and that's where the money goes. Well, thank you.
Discuss some of the space-based possibilities, not just LISA, but there was a proposal floating around for the Big Bang Observer.
Right.
I think they call it BBO.
Yeah.
And just other possibilities you can see out in the next 20, 30 years.
You want me to talk about those?
No, just briefly comment.
Yeah. What Phil is referring to is that besides LISA, there was I think the most significant proposal was the Big Bang Observer. That's something that Sterl Finney and a small group of people at Caltech put together. And their idea was, what would you need if you wanted to see the primeval cosmic background of gravitational waves that is being seen by BICEP, or the equivalent of experiments like BICEP. And it turns out, and look at it in the tail, out at the high frequency tail. And there is a tail. And it turns out that needs techniques which are so much better even than what LIGO has right now, that it's way off. In other words, what you do is you have to, the difference between LISA and the Big Bang Observer is the following. LISA is a thing that's specially tailored to do exactly what they're saying they're going to do. They don't do interferometry by holding things steady. They do interferometry by letting things move and tracking the movement. That's a very important difference. And their whole sensitivity is 10 to the minus 12 meters kind of sensitivity, but with baselines 5 times 10 to the 6 kilometers. That's where you win, especially since the times that they're looking at are so long. In order to do the cosmic background, you have to have the sensitivity better than what you have on the ground in terms of not 10 to the minus 18 meters, but 10 to the minus 19 or 20 meters. And still huge baselines. And now you're really doing something. You're combining all the hairy parts of trying to make LIGO work in space. It's a very different project. And it comes, I think, let's hope LISA goes. Let's start there, okay? Now, there is a project in Japan, which is sort of, it's called DESIEGO, I think it's called. We're trying to do LISA around the Earth instead of at the Lagrange points of the Earth-Sun system. And that, we priced that. It turns out that I was on a committee with Ned Wright that looked at that, and it didn't look any cheaper than LISA, really, by a lot. LISA is 2 billion, sort of, if you went in round numbers. And that was around 1.5 billion. Let's say 5 billion, sure, but it's not what the Japanese thought it would be, somewhere in a couple of 100 million. This is not.
But BBO, wasn't BBO shorter?
Pardon me?
Wasn't BBO a shorter baseline than this?
It was shorter than, yeah, it's shorter because they want to get the higher frequencies, yeah. But that doesn't change it. It's still 3 satellites with enormous power lasers, servo systems up the gazoo. I'm scared of it, to be honest with you. I mean, the other, LISA is a beautiful, thought-through example of just what might be possible. That one isn't. That was a nut case, I think, as far as
I read about all the blind injections that LIGO did.
Yeah.
And I find it very, very fascinating.
Well, you find it fascinating, and it caused us a lot of trouble. And what he's talking about is, well maybe this has to do with every one of us who was on LIGO. When they saw that waveform, okay, and we saw that waveform on email, if we weren't at the sites themselves, we saw that within hours after it happened, okay? And the filtering that was done, none of us believed it. And all of us who were at different places said, yeah, that's just a goddamn blind injection. And it turned out, it took a while to get rid of that notion. It turns out that there was no blind injection. They weren't ready yet. It was just a few days at the end of an engineering run. We were not yet into the actual science run, which started 6 hours later. Okay, and people had not yet practiced even putting in the signals. And one of our deepest worries was not that at all. At the end, it's easy to check, was it an injection? Because you know where the injection point is, and even though it's encrypted in some ways, you can always get at it. No, our deepest worry was that it was a hacker. And to me, that sort of tells you something about doing an experiment in our epoch. That you would think that somebody could sneak in from the outside, get through all the protections of your computers, and put a fake signal in because it made such fun for them. And that took a long time to get undone. I don't want to go into it as a big story, but with that, and I'll be honest with you, we don't have an explanation that is absolutely so solid that you could bank on it to the point of your own life. But you need the hackers, if it's a group, to have such an exceptional understanding of the experiment that it gets so unlikely that it's almost easier to say it's a black hole.
So there is a rumor that you were overruled in telling them not to take data until when they were supposed to begin.
No, I didn't do that. No. Maybe I don't understand your question.
There was a story that you were worried about something in the instrument.
Oh, no, that's a different problem. Oh, you want us that story? Yeah, that story is true. And there were two stories. There were two stories like that. We could have missed this. I mean, this one gold-plated event, we could have completely lost it. And one of them was from well, I'll tell you my story, the hell with the other one. My story was that I was sent down to Livingston by Peter Fritschel, who was the head of commissioning. And they said, you got to fix a problem down there. There's RF interference and in fact it was. There was RF, and it's one of the scarier things, is RF interference. That here, just give you a little detail about what you have to worry about. We are tightly connected together. The two sites are tightly connected by GPS satellites. So, in other words, they're held to within a few microseconds of each other. Okay? So if you have oscillators that are, first of all, driven by GPS, so that they will be, you could have it that you would make coincident signals at the two sites by having leakage of RF. And that was the worry. And so when I got down to Livingston and I looked at the situation, I'm an old ham, so I know the FCC, and I tell you, the FCC would have shut us down. I don't know if any of you are hams in this room, but if you have too much harmonic generation and other crap that you're putting out, they come and shut you down because you're interfering with everybody's reception. Well, I went down there and I turned on the spectrum analyzer, and I couldn't believe my eyes. And there was so much crap flying around. And so I called back and I said to Peter, look, this is a mess. It's going to cost me probably a week to fix this. I mean, I'm going to need another guy. We're going to have to do this together. All the transformers are leaking. The cables are not good. A whole bunch of stuff has just been screwed up. Peter then went to the people who were doing the run planning and said, yeah, but we have all these people coming to the sites. I mean, they're on a train already. They're coming from Europe. They're coming from China. You can't stop the run now. And thank God that won. You're right. That's it.
Yeah, so you have a lot of data from your run last fall, which is probably being analyzed.
Right. Mm-hmm.
So has a decision been made? Are you going to announce each detection as it's...
That's a good question, and I wish I could give you a straightforward answer. I had the same problem with you guys in Berlin. I can tell you this much. There is other data, and there are most likely other sources in the data. And what's going on right now is there is a big effort going on to try to... Look, let me put it this way. None of them are as gold-plated as this, and that makes it harder. Okay? I mean, for example, if any of those other signals which I'm alleged, it could be there, like the ones I showed you. I mean, we acknowledged one of them in that curve. That had a signal noise of, I've forgotten, 8 to 1 or something like that. That would have been a fight that's unbelievable. to publish that as the first thing. Nobody is the hell with it. Wait till you get a bigger thing. That way, but luckily we're not in that situation anymore. It's no longer the very first one. And consequently, I think that doesn't relax your rigor, but it makes it so that you're willing to accept some mistakes. And I think that's what's going to happen. And these will get published in due time. My guess is that what will be published will be the APS meeting in Salt Lake, which is, I don't know when that is, but it's April 19th or something like that.
There'll be some announcement.
Oh, there'll be an announcement, yeah. And it's not that every one. I mean, I think one, if there is more than one, there'll probably both be one. But I think there's at least one that's very interesting, I think, if it's true. And that's being checked on right now. Yeah.
So Ray, the one question I have is the signal to noise at the gold plated event.
Yeah.
Was it adequate, not as a first event, but today, or when you start to run again, would it be adequate signal to noise if you could leave it in a single detector?
That's a very good question, and I've asked for that analysis. What he's asking for is something perfectly reasonable. You have it doubles the amount of data.
Right.
It doubles the amount of data, and I've asked for that. The data analysts are not, this is not on their top list of things, but it will be done. Okay, because you're quite right. It's now that we know what the signals are, and then maybe you may not have to rely. I mean, you will have far less significance, but it still will be an interesting signal. That's right. Yeah, something like that. You're right. Yeah.
Please.
So, if I heard you correctly at the beginning, you said that leading scientists in mid-20th century misunderstood the effect that a gravitational wave would have on propagation of light.
Yep.
Correct? So that's fascinating, right? I mean, did they just somehow make a mistake, or are you saying that GR was not actually a complete theory until fairly recently?
No. That's a nice question. Thank you. What he's asking, if you heard it, is was it a screw up in the theory that you didn't have this right, or was it people not understanding the theory? And the problem is this latter. The people didn't understand, and many of the people who were objecting when that came up were people who were working on bars. And they said, look, I mean, see, why could I not teach in that course the Weber thing? By the way, it's a perfectly legitimate thing, but I had by that time tutored myself into thinking that there are no forces left in gravity, okay? This is the way I looked at it. It's all geometry, okay? I mean, I was a young person, and I looked at that, and I bought a hook, line, and sinker. And so what happened is that the way you would analyze a bar was quite complicated to me. I didn't feel I understood it, because the way you do that is you don't use the H, you use the curvature tensor, and convert that into a tidal force. That's where you do that, and you use space as being Euclidean. So you don't write H that way. You use a new field. You do it more like Weinberg's book, or I know other people have written books on. It's not. You don't use geometry. You use a new force field, which is a tensor field, and just use it and believe it as it stands. And I didn't want to do that because I didn't understand how the interaction between a gravitational wave and a bar worked. Well, it turns out it is just, you can think of it as a tidal force. So what happened is that those people who had taught themselves that. And there's another step that you ought to know. And this is really in the education of all of us. When all this took place in the 60s and 70s, most physics departments did not have a course in general relativity. It was all in mathematics. I taught the first GR course at MIT since 1930, in 1967. There was no GR course.
What year was it?
67, yeah. And there was no basis. People had not learned any GR. GR became something to teach people again when it began to do experiment, when it began to have results in astronomy. And cosmology, of course, yeah. And so that's the transition that took place. So a lot of people were ignorant of what was in the theory, okay? And that was the problem. And what they did is they mixed up the two approaches. They mixed up the geometric approach with this tensor force approach. And they came to the conclusion that, if you do this, you're not going to see anything. And that was held by, I would say, 80% of the people working on bars.
So,
But even Einstein got it.
Well, Einstein had it wrong for other reasons, yeah.
So when was it first known?
What?
When was it? So you're saying there was a large group of physicists that didn't really understand this. Presumably there were at least a few people that did understand GR well. when was the first person to have a fully consistent theory of GR in the sense?
It's not a system. GR has not gone bad. It's the people understanding the thing that was always difficult. And when you learn GR for the first time yourself, if you find out that the coordinates don't mean anything, and if you bank on the coordinates, you're in trouble. You've got to find invariance, and you've got to find out what does not change from one coordinate system to another. And that's something that people didn't really realize. And there was nothing wrong with the theory. Please do not get that. There were other problems. There was misunderstanding of the theory. It was sort of like, the first time you sit down and read GR, you read it in some popular science book or something silly like that. And you just don't get the whole idea. And that's what the trouble was. Nobody sat down except Joe Weber himself. I'll guarantee you, all the people who were working, Dave Douglas, Tony Tyson, even Heinz Billings, probably never bothered to even look in a general relativity book like Peter Bergman's book, or Landau and Lifshitz, who had it very straight. They never bothered with that. It's too complicated. The hell with all that tensor crap. Yeah.
Great talk.
Yeah.